My name's Sean Boyle with SIU Automotive, and today we're going to look at the electronic VVT system, the VVT actuators that are found on Nissan and on some other vehicles. We'll look at that later too. So first, let's, hold on one second, I gotta click on it here. Okay, I knew that was going to happen. First, let's take a look at just how a VVT system operates. The purpose of a VVT, variable valve timing, on these engines that we have, which pretty much every engine uses VVT of some sort, is to increase the volumetric efficiency of the engine and also to create possibly an EGR effect, and that allows us to eliminate the exhaust gas recirculation valve that we've had on engines for years that reduces the nitrous oxide emissions. But so they can use variable valve timing to do that. And I say for the most part because this Nissan VVT that we're looking at today, it actually still uses an EGR. So it has a VVT on the intake and the exhaust and also an EGR. So anyway, but yeah, we pretty much use it for this EGR effect, and we also have this increased volumetric efficiency. By altering when these valves open and close for the different RPM ranges and load ranges that we have on the vehicle, we can optimize the volumetric efficiency for that engine. So VVT, you'll find a lot of times, in a lot of engines, you'll find that they're found not only on the intake, but also on the exhaust. There's some of them that have exhaust only or intake only, but a large majority of engines will actually use them on the exhaust. And in this vehicle right here, for example, here's a vane type VVT, and it's this. I took this picture at an auto show because all chromed out, looked all pretty. But if you take a look, this is the cutout section right here, and this is the kind of the vane assembly or the rotor assembly that's connected to the camshaft, and then this is the camshaft sprocket. And what they'll do using solenoids is they'll, on a traditional type hydraulic VVT, they'll balance the oil between this side right here and this side right there, and they can alter the camshaft in relation to the sprocket. That works out really well, and you're limited to the amount of range that you've got, but they really don't need a whole bunch of range to tweak the cam timing and make it beneficial. You'll also find that they use it in cam and block settings too. So here in this engine, this is a cam and block, and they still use a VVT. Now, since we don't have a separate intake or exhaust cam, the VVT is going to operate both intake and exhaust lobes together. But just to let you know, a lot of these cam and block engines utilize VVT as well. So the different types of variable valve timing actuators that we use, this is the old school design. In the early 2000s, Lexus, even GM, a variety of manufacturers, they start out with this helical gear design. And you can see the teeth on here is got kind of like a helical shape. They're cut on an angle. And then that gear is also listed right down there, or shown right down there. And what they do is they move a piston. This piston assembly will move forward, wrong direction, will move forward and back along that helical gear, and that'll actually twist the cam sprocket on the camshaft. That allows you to change it. That's an old design. It was like one of the first designs they came up with, and it's slow. It also has just a limited range of adjustment that they can change the variable valve timing, because if you take a look, you're really limited by the angle that these teeth are shaped. So from one extreme to the other extreme of the angle of the tooth is only the amount of twist that you're going to be able to get on that camshaft. So more common is going to be this vane type, and here I've got an illustration. This is that rotor that's going to be connected to the camshaft, and then over there is the housing where the sprocket attaches, and that's going to allow the cam and the housing or the sprocket assembly to operate differently. And what they do, as I mentioned before, is they balance oil on either sides of the rotor lobes. And in this one, they've got 4 rotor lobes. You also notice right here, kind of up on top, this green little plunger right there, that's a locking mechanism. And what that's going to do is when you shut the vehicle off, since they're using oil pressure to manipulate this, when you shut the vehicle off and all your oil pressure drops off and drains back, especially if it sits for a while, they use a spring-loaded lock pin to latch that cam rotor into the cam sprocket, so when you start it up for that split second before you have oil pressure, that you don't have this thing rattling around in there. So if you have an issue with the vehicle that rattles when you first start up, you might have an issue with this cam, this plunger and the spring. It's that locking mechanism might not be working. And up here, just another picture of that vane type. You can see that, get my finger, I'm new to green screens here, so I'm not the weatherman, haven't been practicing this on Channel 3, Jim Razor. But anyway, if we put oil on one side or the other by how much we're balancing oil on either side of this, we're going to be able to determine the position of this rotor within this housing. And you can see the amount of travel that cam's going to have, or that rotor's going to have, is from this extreme all the way to that extreme. That's the adjustment that we have in this variable design. And why do we do it? And this is kind of an illustration right here that you can see that this, like down here, says top dead center, so that's where the piston is going to be at top dead center. And you can see on this little hump that we have right here, that's the exhaust valve opening and closing. And then on the intake stroke, we'd find the intake valve opening and closing. And this illustration up here is showing, okay, yeah, we've got these valves and they're opening and closing, but when they open and close is going to determine fuel economy, it's going to determine performance through volumetric efficiency. And since the engine isn't static, always operating at 1 RPM, it could be at idle or it could be at redline, that in an ideal world, we'd be able to adjust or change this type of timing because the events, what's happening in the engine, changes as the engine's revved up. And they have different requirements. So they came up with this variable valve timing to enhance that, make it better. And you can see in this little illustration here, they're showing where the little dashed line is. That's where the intake valve in this example can move all the way over and advance itself so much, even onto the exhaust stroke. And that's how they get that EGR effect. They let some of the exhaust gas get into the intake. And also because of the way the pistons travel, when a piston's moving up in its bore, it's moving a lot of air on the exhaust stroke. And once it gets close to the top and crosses over and starts to go down, there's very little air movement. So like this little graph here shows the actual volume of air increases quite a bit as the piston travels up, and the same thing holds true as when the piston is traveling down, it's actually moving down, it's actually drawing in quite a bit of air. But during that top dead center and that bottom dead center range, there's not that much air movement because the piston's not moving that much. So if I alter the cam timing to take advantage of either inertia, like at high RPM, when there's a lot of air running into the engine, I can actually retard the intake timing and let the inertia help fill the cylinder up with air. We'll see some of that coming up. Because right here, this document here, this theory right here, comes from Toyota in their training documents. And this black line right there, that is the exhaust valve opening. In relationship to top dead center, there's top dead center and there's bottom dead center. And then this kind of white boxed marking is the intake valve opening. So in this situation, we would look at the period where the exhaust valve closes and the intake valve opens. That's what we would call overlap. And during starting and when the engine's idling, you can see they have very little overlap. They don't have any, really, for the most part, overlap. So what they're doing is they're retarding the, it possibly can. And by doing that, we actually build up less pressure in the intake. Low engine speed, but light to medium load, what they ended up doing, they still have that intake retarded. Now, this is also variable. It's not like it's just going to be in one of these positions or the other. It's just in a general sense, they're going to retard the intake timing a little bit or keep it in the retarded mode. And you'll see when they rev this engine up, they'll advance it a little bit more. But the exhaust, what they do, instead of having it in the most advanced, they start moving it retarded. And the reason why is because now I can get this little overlap section here where I can get some of that exhaust gas and push it into the, into the combustion chamber and push it into the intake. And that's that EGR effect. Exhaust gas recirculation, EGR, it was brought about a long time ago for emissions purposes. Exhaust isn't a fuel, and exhaust, it doesn't promote combustion because it doesn't contain any oxygen, so it's inert. And if we mix exhaust gas into the intake mix coming in, it basically takes up space and lets our engine almost, it doesn't change displacement, but it actually acts like it's a little bit lower displacement engine. So by bringing in exhaust gases, will bring in less air and less fuel, and then you'll have a more fuel efficient vehicle. So better fuel economy and emissions, and that's low engine speed, light to medium load, just like when you're driving down the road. Now, in low to medium engine speeds, heavy load, what you're going to see is that they advance the intake now. They're going to bring that forward. And you know, they do that because of this reduced blowback. They don't want some of that air when that piston's coming back up on the compression stroke to push back into the intake. They want to advance that cam so that way we don't waste any of that air fuel charge that's coming in by pushing it back into the intake. We'll just get a solid you know, air fuel mix. Because at this point, we're not as concerned about the EGR effect. We want more performance because we're under heavier load. And they also, like I said, they advance the EGR, the exhaust more, and that's going to reduce the EGR effect but allow for better volumetric efficiency at that engine speed. Now, the high engine speed, high load, that's the situation. Now, it seems kind of weird because the overlap is smaller, and a lot of like those of you guys that do performance stuff are like, well, at high RPM, you want larger overlap. But since they have the ability of adjusting these things, they take advantage of the intake stroke to kind of get as much air into the cylinder. You don't want as much exhaust in there. You don't want really any at high RPM, high loads. So what you're going to do is you're going to have that intake valve open a little bit longer because think, we're talking about high engine speeds, so this engine's moving a lot of air. And when this piston's coming down and that intake valve's open, there's going to be an inertia. There's going to be a certain amount of like a forced, I don't want to call it forced induction because we don't have that in this little example here, but this inertia, this momentum of fluid going into the cylinder isn't going to stop the second that piston hits bottom dead center. It's going to keep going. So they take advantage of that by going ahead and retarding that ignition timing or the cam timing as long as possible to let that inertia fill that cylinder and kind of pack as much air and fuel in as possible. So increased output, that's the reason why they're doing that. So kind of a run, just a brief breakdown of the reason why they have VVT. And like I said, sometimes you'll find it on the intake, sometimes you'll find it on the exhaust, sometimes you'll find it on both. And they're trying to increase volumetric efficiency and improve emissions and improve fuel economy. So what about this Nissan actuator? We're going to look at that because they do something different. They don't balance oil on the intake back and forth. They control everything electronically. So let's walk over to the bench and we'll look at that. Hello again, and it's me over at the bench. I got some VVT parts sitting up here. We're going to zoom in on a few of these things and look at it. This is the traditional, basically the traditional system that they have, and it's a just a phaser or hydraulic VVT actuator. I have already taken this apart, obviously. That's why some of the screws are missing and so forth. Let me show you before I completely take it apart that there is a lock mechanism that's in there, and I took it out so that way we can actually see how much movement that cam has. So you can kind of see that's what the cam's going to be attached to. There's a little dowel pin there that lines it up. And so that's the amount of movement that I'll have on this hydraulically actuated system. Not a lot, but that's really all they need because they're obviously they've got to keep the intake valves opening on the intake stroke. And you know, I could have that electric actuator, there's actually, it can go 360 degrees around. They're not limited by anything. But this design here is going to be limited. You're going to need a certain amount of metal to make this stuff work. And so here's the inside of it. And you can see I've got I took the screws out so it doesn't work with the cam, but this is the part that would attach to the camshaft. And then of course my sprocket's up here. So when my chain is driving the camshaft, the computer can manipulate the oil that's going to exist on either side of this vane and actually position that exhaust cam, in this case, in whatever position it needs. Now, I mentioned that there's a locking mechanism, and the way that Nissan does it in this vehicle, because this is off the same engine, they use the hydraulic actuator on the exhaust and the electric on the intake. They actually use a vane, and that will lock that mechanism so that way it can't really spin. And they use oil pressure to pop that thing unlocked. Like I said, I left this out so that way I could spin it, but there's a spring that pushes, that kind of lives in this little slot right there, and it pushes this into the locked position. And when they use oil pressure, once the vehicle starts up, they have an unlocked solenoid. They have a separate solenoid, and it will push this thing unlocked, and then once it's unlocked, I can get my full VVT action. They basically want to do that because they want to make sure when you first start this vehicle up that you're going to have, you know you're not going to have any oil pressure. When you first start it, this thing might go clack, 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 clack until there's oil pressure built up, and then you're all good. But that's not the ideal situation, having a lot of noise. So if you have that when you first start a vehicle up and you hear clack, 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 and then it goes away almost immediately, you probably got a cam phaser lock mechanism that's bad. These also, and I don't have it on there, they have a spring assembly, and that spring assembly is there to keep this thing loaded. So when you shut it off, that it's going to find its way to that lock. But this thing gets latched in there. It's kind of a pain in the butt to put on. But I wanted to show you guys the traditional system first. Matter of fact, when you look at the cover that goes on the front of the engine, that's what these two solenoids are for right here. These are one of them is the oil control solenoid that allows the retardant advance, and the other one's the unlock and lock mechanism. Not all manufacturers use a separate solenoid for unlocking the VVT. Most don't. Most of them just use oil pressure going to it to unlock it. So once there's oil pressure in that phaser, it pushes that back. But Nissan, for some reason, felt they needed that. So let's focus on this electronic VVT system, and it's an electronic actuator. It's pretty neat. If you look here, we've got these contact rings that go all the way around, and we have a mechanism that lives on the outside of the engine, and it has brushes. It's pretty wild. Matter of fact, I can show you. This is that engine right here, and when you look at the front of the engine, I have that cover assembly off of it. So that would live kind of in here, covering that up. So that is the VVT actuator and the mechanism. And just to also show you, probably could have get a peek at my green screen back there. I've got a battery pack here, so we can make some sparks fly, which is always fun. So you can actually see it work. That's the travel it has. You might be, actually it looks like it's going really far, but each rotation of this dial that you see here is only 6 degrees of, which I calculate. I don't even know if that's right. You'll see how I came up with that. This plunger right here is is part of a sensor, and we'll look at that separate. But there is actually 3 different parts they look at. They look at this outer edge, so they have 3 outer points. Then they have 6 legs, and then 6 inner points. There's actually quite a few little things, and they all measure that off of this. If you look right here in the middle of this plate, they got some really funky solder joints and wires, and you can see if I can get the glare to hit it just right. But they have some kind of advanced circuitry in there that's what it does, is it picks up on these little pieces right here. And it can tell precisely the position of that cam and to the sprocket and the cam relationship. Probably not cheap. So going back to our setup here, I could do that same check on the bench here, looking at this actuator. It is whoa, scary, huh? It's a torquey little guy. All right, I bound something up, so now we definitely have to take it apart because I probably broke something in there. All right, so let's take this thing apart to a point. By the way, here is that sensor that I was talking about that has the legs. We got the 6 inner points, 3 outer points, and then the 3 or 6 legs of this. And they say, and they've noted this in about 100 different spots in the service manual, that if you take this off, you have to replace it. I don't know why. I mean, it's got an O-ring on it. It's made out of plastic. They don't tell you when you pop it on. It doesn't have any special instructions. This part here clips onto the lip on the cam. So when you push it in, it kind of snaps into place. So I'm not real certain why they're so adamant about people changing that, but they are. There's a Torx that goes in there to loosen it up. Very nice looking well-built camshaft assembly. Matter of fact, this is on the end of the cam here, you can see the drive for the high pressure oil pump. They got the cam sensor teeth. They've got cam sensor teeth even on the intake. Even though they can measure it using, I guess they can measure it using this outer housing. Okay, so I got the bolt out. Now as you can see, I've taken most of these screws out already. So it should come apart a little quicker. There's a possibility I might have to press something off here. I doubt it. I actually spent some time and opened a bearing up that will kind of interfere with our little disassembly here a little bit. So pull this little, there's a little, that's the part that controls how much movement you have in this cam. You know, I only can go from that extreme to that extreme. If I didn't have this on there, that cam could just spin around and around, or the motor could just spin around and around. There would be nothing stopping it. Now this is the part that can sometimes be difficult to pull out. There's a bearing in there. I was kind of hoping, I actually spent some time machining on that to get it to come out easier. So I might do something that's totally not recommended at all. Tap on this to see what happens. In all reality, this is not a serviceable part. We're just really taking it apart just to see how it works. Okay, well I can pull this part out and show you. These are the brushes. They and they have springs. So this thing actually uses brushes, just like a starter motor or something like that. So they go from these contact rings to these 4 brushes. They were a little difficult to put in, except I made these little clips, and they're just pieces of stainless steel wire. And basically I just pull on the, they're real thin stainless steel wire. I don't know what size. It's welding wire. So that way it kind of holds these in there. They haven't launched out and injured me yet. Probably should be having safety. I really should have safety glasses on. I forgot to put that on again. Erica, if you're watching, would you expect anything less of me? I'm a bad example. So you definitely want to make sure you keep the snap ring or the springs in there. That's obviously what pushes them out up against the. Okay, that's the one. Needs a shorter one. Here we go. There's one of them, for some reason they got that notch right across from it. Maybe it's an ID part, I don't know. But so I actually had to make one of these guys just about 1/8 of an inch shorter than the others. And there's my spring, it fell in there. I've only taken this apart one time, so if I do something wrong, chalk it off to inexperience. And like I said, I don't think anything on this is serviceable. So there you go. That's just sitting there, ready to be installed. I will put this off to the side for now because I'm not at that point. And there is, like I said, there's a bearing that lives in this assembly. Matter of fact, I can do this real quick since all these parts are, if I'm spinning that motor, it takes a while. Matter of fact, now that I think about it, one rotation of that motor is definitely not 6 degrees. Can you tell this plate's moving around? I'm spinning it. Lots of rotations just to get that camshaft to spin around. Slow, very slow. I'm gonna go be all brutal on this thing and maybe try to get a screwdriver on each side and pry it apart. Like I said, I spent a little bit of time honing out this bearing that is the piece that's giving us a little bit of issue right now. So it should have come apart easier, but you know, nothing ever comes apart easier when you're doing this stuff live. And there we go. That wasn't too bad. So this is the part that's moving the assembly. Let me try to keep this in focus. If you take a look, we've got a bunch of these little needle bearings up here, and they all fit into these little, and it's hard to tell probably on the video. If I get too close, it might not zoom in, but see, it looks like there's splines. Those aren't splines really. Those are meant for the rollers to sit in. And believe it or not, I sat there and counted all these rollers. And there is 30 rollers and there's 61 little notches. So that's where I got my 6 degrees, but I think I did my math wrong. Every time this thing walks around, it moves over one roller, basically one notch. If I've got 60 notches, I just assumed that one rotation would have moved me 6 degrees. But whatever, I'm wrong because there's no way that was moving 6 degrees. So yeah, the motor assembly that we have in here is pretty neat. Somewhere I thought I had a socket that fit in here. I don't need it. I think I honed that out well enough to push it apart. Because what they're doing to get this thing to happen, and I know I'm kind of jumping around here a lot, is this part right here is not centered. This is the part that this bearing fits around. You can see it in this angle. See how fat it is right there? And on the other side, how thin it is? It's very slight, but when we have this bearing on there and it rotates, it actually is going to make this bearing kind of do this, kind of spin around elliptical. And what that's going to end up doing is it's going to cause it to walk around these rollers elliptically, and it kind of forces these rollers to take a step over every time it goes around. So as this thing's spinning, it's forcing this little cage assembly to take one step around. And since one side's going to be attached to the camshaft and one side's going to be attached to the cam sprocket, we're changing the relationship between the cam and the sprocket, one little roller at a time. And it's infinite between those rollers because I can do partial roller with a partial rotation. So they can get real fine control with this. And that's the reason why when you put this together, you can see that. Let's see if you can see that bearing wobble in there when I spin it. It looks like it's out of, I go slower. Look at this gap right here when I spin that. See it go close and far, close and far. Try to catch that light right in there. But anyway, that's how it works. So I got this thing spinning back and forth, and pretty cool. All right. I don't know if anybody's posting up or watching this at all. Hopefully some people are watching this because spent a lot of time setting it up. But if there's any questions, feel free to ask. I don't know if I can answer them because this is a new system. I got some information from Nissan, and they had some good kind of technology bits. There's really no service bits that are about it. And we don't have a vehicle, but what I'm going to show you here we're going to just use one of our vehicles that we have here at SIU. And I'm just going to show you the VVT system and where it's laid out, and then we can look at some data that's on a scan tool, because I'm sure the data is going to be similar or the same between this and this Nissan vehicle, which this is found in the Altima, and probably other vehicles as well. But I know the Altima has this, and we'll go through and let's take a look at the this Chevy Sonic, or no, what is this? The Cruze, the Chevy Cruze that we got. Pretty common engine. And my camera person is going to come over here, Mike Bierman, the elusive Mike Bierman. If you take a look, this is where the VVT actuators live on this. We've got our exhaust actuator and our intake actuator. Made in Germany, it says right there. Well, at least it says Germany. I don't know if I assume that's made in Germany. And so it's going to, they've got dual controllers on that. Looks pretty easy to get into and change it, like at least these actuators, the electronic side of it. If you needed to change those cam phasers, you'd have to take the engine pretty far apart because you have to get the chain off, take the phasers out, so you have to probably pull the front of the engine off. So let's go take a look at some scan data, because the typical complaint that you might have with a vehicle that has VVT issues is, one, you might have a diagnostic trouble code, and the diagnostic trouble codes could either be circuit codes, or sometimes they are related to the variance. They might say the desired and actual camshaft positions might not match. And I don't know, can you see this on the scan tool if I hold it right? So this is on our snap-on tool, and that's probably pretty good. You might back up a little. There we go. Yeah, that'll be fine. You can see I've got my exhaust cam and my intake cam variance. And I have my exhaust cam angle, intake cam angle, the commanded percentage for their solenoids, are then the desired angles. So that information is really good to have, because you don't, having the angle by itself, you don't know if that's good or bad, but if you could see what the computer wants and then actually check to see what you're getting, you need to back up. I think you're blurry. You can actually go through, and the variance will tell you how far your angle versus your desired is. So I'm going to start this engine up. Now remember, in startup mode, they usually, they have this thing set in a position so that way it's easy to start. So, and then if it's cold, they actually might run it in that same sequence there for a little bit. You don't want to get too close. They can see fairly well here, looking at that monitor. So like right now, you can see the exhaust cam angle's changing. It's 7. The command, now it's 8. The command is 8. Now it's 9. It's slowly changing, 10. You can tell they're doing that as this thing warms up. It's almost immediate, of course, but it's you can kind of tell that they're going through the desired and actual match, which means the variance numbers are the same. If the variance is like, say, 3 or 4 or 5, that's when you know that the desired and the actual aren't matching. Now I'm going to go in there and let's see if I can position this so it won't glare out on you. Here, let's see if I lay it under the hood. That's pretty good. If you take a look, I'm going to brake torque it and you'll see those numbers change. So those numbers changed, kind of give you an idea that they do have action. One of the other things that we can do, if we can go through and actually control these actuators. So if I back out on my menu and I go to functional tests, I can actually pick the camshaft actuator. I can check my solenoids, but I'll have to have the engine off. If I want to go through and just say, hey, is this thing working right? I can go through and pick either the exhaust or intake actuator. It says, make sure the transmission's in park, blocked wheels, all that stuff. Some safety screens there. And now, glare out the screen. You can see up here I got the word test. So if I hit that, I can go through and change. I'm in the exhaust cam actuator. So my actual and desired and the variance is 0. So I can go through and I'm going to add to it. There's 8. You can see the variance is still at 0. I've got 8. And desired is 8 and actual is 8. 12. Switch is quick. So you can see the variance change just for a split second. You're probably going to get too close. That thing doesn't like to be close. And now it told me my 30-second timer's up. They don't let you do it forever. I can check my intake as well. Hit test. And I can change my... So I'm at 0, 0, 0. I'll have to scroll down to get my variance there. Oh, went too far. They don't have it on the same screen, but they're not letting. Yeah, they're jumping one screen at a time. Oh, my time expired. But my point is I can go through and check the intake and the exhaust cam actuators for electronic or for the hydraulic operation. If they were slow or sluggish, then I would be curious, okay, do I have maybe oil contamination? Because what can also happen in here is if you've got a customer that's not taking good care of their vehicle, they're not adhering to the oil change intervals that they should, all that gunk gets kind of caught in either the oil control solenoid or the cam phaser itself, and then that can cause a sluggish or slow moving cam phaser. Also, if I have low oil pressure, go ahead and shut the vehicle off. This thing's got I think a vacuum leak. But so this thing will, if I have a poor oil pressure, I can obviously have a problem because these cam actuators are operating off of oil. And now, if they didn't have any control at all, and I'm sitting there operating, I can't get anything to move, I could go through and check the solenoids, and that's where the other function test was. Check the cam actuator solenoids, and what it's going to do is turn them on and turn them off. And you can go right there at the solenoid and check to see if you're getting the proper command. If you're getting the proper command but not getting action out of the solenoids, then you know solenoids are bad. So this was just kind of a brief rundown. I don't know, and I have to assume the 100%, I can't say for 100% that the Nissan's going to have the exact same functions for testing in there, but I assume it's going to be something similar. I don't have one of their vehicles to check though. So one other thing, we're going to go back over to my PowerPoint. And I'm going to show you guys a couple things on this here PowerPoint. I have to find my clicker. And for some reason... So does Nissan, are they the only ones that have this system? And they aren't. I don't know why I came across this. I was researching this system and I went to Honda. I was just going to look to see if they had some good animations for VVT. And lo and behold, they've got what they call their brushless electronic VCT. It's on their intake. And 2014 is when they first came out with this, and it was on their plug-in hybrid, their Accord plug-in. But now if you just look at their Honda hybrid, they use it on the intake. That's the only thing they have. They don't have an exhaust cam phaser. They just use this brushless electronic phaser for their intake valve. Now I don't have information on it other than what's in the service manual. One of the things that's interesting, if you take a look here, because I was trying to figure out how they're doing this brushless, because we saw how that Nissan did it, and they use brushes to make power going to that the motor assembly in that cam phaser to rotate that little geared mechanism or that little roller bearing mechanism. So how are they getting electricity in there to do that if it's brushless? And then but through reading, and there's very little information on it, it doesn't look like that's how they do it. They utilize this motor that's attached to this assembly right on the outside of the engine. And by the way, this has the module to operate it built into it, whereas Nissan, it is that sensor assembly that I had on the outside, that is like its own little smart system there, but they have a separate module, separate from the PCM, to control that phaser, and it's mounted under the hood, kind of I think along the fender well or something like that. Whereas Honda, their system is all incorporated right here in this mechanism. They got the module and everything, it just receives communication information. And they spin this little motor right here, and that motor fits into the actuator assembly. So when that motor spins, and it has to go at the same speed as the engine, either a little bit faster or a little bit slower, depending on what the cam timing they're trying to achieve is. But they're doing something similar but different. Probably hate hearing that, but they walk the mechanism around. Instead of using roller bearings like Nissan did, they're using a little gear, and they call this a planetary gear. So you have kind of this motor that lives in the middle of the shaft. It's going to influence this center ring, which is going to cause this little toothed or cogged wheel. I guess they'd call this a planetary gear right here, and then the outer part, the internal gear. And it's going to walk one tooth at a time around, so it's going to be offset. You can see it's going to wobble just like the Nissan system does, and it's going to make that geared wheel walk its way around forward or backward. The one thing I find that's interesting on this though, unlike the Nissan, once they move something, they could turn it off and it's going to kind of keep that actuation, it's going to keep whatever valve timing it's set up. But on this system here, pretty sure that motor is going to have to spin all the time along with the camshaft speed, and it's going to have to spin a little faster if it wants to retard it, and spin a little slower than the camshaft to advance it, and then spin the same speed to hold it. So that's kind of interesting, but it's been around since 2012 2014 for 6 years. They don't have any TSBs on it, so they don't really have much information service-wise or tech news or anything like that I've seen. So I'd have to believe that's not a faulty system or a bad system. This is their electronics. You could see this is kind of like its own little module built in. They have power. They have two powers and a ground. This is a command and the actual speed, direction, and a diagnostic. So all that stuff goes to the PCM, all that wiring. That's on the Honda. And down here you can see it's the same drawing up top here, but this is kind of a drawing of their motor assembly, and it's that they're using a three-phase type system there. And those are the circuits that we're talking about here. The diagnostic, these three go back from the this internal controller, or this the whole electronic variable timing control or valve control. All these three circuits here feed the PCM with information. This is the only one that the PCM provides, and it says this is how fast it wants to go, which is basically going to give you the command for your advance or retard on your camshaft. Only on the intake. And the reason why they're using it on their plug-in hybrid and on the intake is because those of you guys that know a bit about hybrids, the engines, they try to operate those engines more like an Atkinson cycle engine, where they have higher compression ratio, and when that piston's coming up on top dead center or on compression stroke, they leave the intake valve open for like up 90 degrees into that compression stroke. So that way their high compression engine isn't really compressing that much. They're only compressing about half of the total compression stroke. And then you keep the intake valve open for a long time because you can actually push back into the intake and you create low pumping forces and all that stuff. And the benefit of that, as far as hybrid is concerned, is that those Atkinson style type engines were not very good at low end torque. But with these hybrid vehicles, we have the electric motors to take care of the low end torque. So it's a perfect match. We got these electric motors taking care of the low end, and then the Atkinson type engine, which is very efficient, and it works better at higher RPM, and it kind of they're a perfect match for each other. So that's how that all works, and that's the reason why Honda uses it, and they only use it on the intake, so they can sit there and move it between more of a traditional and an Atkinson type engine. And this, as you can see, it's a pretty complicated system here. They've got, I'm not going to go through the schematic or anything like that, but it just shows you all the drive controls that they've got for the three-phase motor, and then the PCM's looking at all the information and all that good stuff. So that is all I have for you. I hope that you guys learned something about the Nissan electronic variable timing, cam timing. And we're going to look at some other Nissan stuff here in the future, near future. We're going to look at their variable compression engine, which I got a couple of those. And we're going to also possibly look at their VVEL, the variable valve event lift, which is like a throttleless engine. But and then we're also looking at a bunch of other things. We're going to look at diesel fuel injectors. That's going to be coming up next Friday. We're going to focus on the piezo and the electromagnetic diesel injectors. And I got diesel instructor extraordinaire, Tim Janello, helping out with that. So it should be good. Tune in, share it with your friends, let everybody know. I know with the COVID-19 going around that we're all kind of limited on what we can learn and the places that we can get information from. But here, we've got a lot of this stuff at the Tech. We want to share as much of this knowledge as we can with you. And so if you have any ideas for topics or something, post up in the comment section or something like that. Or email me, jeepster@siu.edu. And I will see if we have that technology, if we can cover it. And trying to shoot for like little half-hour segments. This one ended up being close, 52 minutes. Oh, well, you know, I get long-winded. But so I will see you guys on the next one.